So in this problem, I need to find the extrema of this function. And one of the things I can tell from this function right away, well, first of all, it's a polynomial. So I know that the domain is going to be negative infinity to infinity. I also know that since it's a polynomial, the graph is smooth and continuous, and there are no poles or vertical asymptotes. So domain negative infinity to positive infinity. I know that because it has a highest power that is odd, and it does not have any negative sign in front of the leading coefficient, I know that the end behavior of this graph is going to be down, up, just like the graph of x cubed, which is the highest power that is odd, and we know that the graph of x cubed looks like that, with down, up, end behavior. This problem is actually a very nice complement to the problem that I just did a second ago, also using end behavior to try and find out where the extreme points are. The absolute maximums and minimums, or the relative maximums and minimums. Because actually in this particular problem, I have no absolute maximums or minimums. I know I have this end behavior that's going down all the way to negative infinity, and this end behavior that's going all the way up to positive infinity. So it's impossible to have any absolute maximum or absolute minimum, since the graph itself, the function itself, is going from negative infinity to positive infinity in its range as well. So we might have some kind of a local maximum or minimum, and we need to see if we do by finding the derivative of the function. So y prime would be equal to 3x squared minus 6x plus 3. And so in order to find out whether there are any critical points, I need to set this equal to 0. And those will then be stationary points, because there are no points where this derivative does not exist. This itself is a polynomial with a domain of negative infinity to positive infinity. So the derivative is going to exist throughout the entire domain of this equation. So I have 3x squared minus 6x plus 3 equals 0. Let's see if there are any points where it equals 0. Well, let's use the surefire method of factoring to see if we can factor this. So I have 3 times 3, which is 9. And are there any factors of 9 which will get us a negative 6? And of course there are. It's negative 3 and negative 3. So I'm going to change this quadratic here into 3x squared minus 3x minus 3x, just basically changing this 6x into two negative 3x's. I'm going to add 3 and still keep it set equal to 0. Now what I'm going to do is I'm going to group the terms. And as soon as I put these parentheses around this back term, since this was a plus and that's a minus, I have to change this plus here into a minus, because I have to distribute this negative sign inside, which would then turn it into the plus that I want for this plus 3. So I've grouped them, and I'm going to pull out of the front group a 3x, and that would be times x minus 1. And I'm going to pull just a 3 out of the second group, and that leaves me with an x minus 1. And I still leave that set to 0. Well, now I have this x minus 1 in both terms here. So I'm going to factor that x minus 1 out. And that leaves me with something times x minus 1 times 3x minus 3 equals 0. So I can see for this piece here, if x equals 1, that's going to make everything equal to 0. And what do you know? For this piece here, if x equals 1, that means everything's going to be equal to 0. So I know my critical point is going to be at x equals 1. So that's going to be the point 1, what? I don't know. Let's go back to my original function up here and plug in 1 for x. So I would have 1 cubed minus 3 times 1 squared plus 3 times 1 minus 2. So that gives me 1, well, minus 3 plus 3, those cancel out. So 1 minus 2 is equal to negative 1. So my critical point, which is also a stationary point because it makes the derivative equal to 0, is at 1, -1. Now I only have the one critical point, and that's here at 1, -1. So I'm just going to place it right there. And I know that at that point, and that is the only point on this graph where the derivative is equal to 0. I proved that algebraically. So if I know that I have n behavior that's down, I know this graph is actually from the left to right is coming up, and it's going to get close to that point. And for that very instant, right there at 1, 1, 1, -1, the derivative is equal to 0, but then it turns and it has to go up. There's no way that I can have another point, because if I had another point, I'll do it in a different color, the graph would have to go like this. It would have to go, hit the point, go down, and then up again, and then I would have 2 points where the derivative is 0, and I only have 1. So if I only have that one point where the derivative is 0, I can see that that's not a local minimum, and it's not a local maximum. It's just an instant point, just like in the graph of x cubed, where the derivative is 0, and then it continues up positive. So this particular function here has no extrema, no maximums or minimums, either relative or absolute. You could analyze this numerically. You could take the function up here, and you could say, well, how does it behave as x approaches 1 from the positive side and as x approaches 1 from the negative side? Well, positive side, negative side. I mean, so I could go ahead and well, actually, since I know there's only one turning point, I could plug in, if I make this into a number line instead, let's do that. That might look a little bit nicer. So here's a number line, and here's 1, 2, 3, -1, 2, 3. I want to approach x from this side, and I want to approach x from this side. Now I know there can only be one turning point. I know there can only be one possible maximum or minimum, because there's only one place where my derivative equals 0. So I can evaluate this function, say, at x equals 0. So if I evaluate it at x equals 0, so let's go f of 0, that would equal 0 cubed minus 3 times 0 squared plus 3 times 0 minus 2. So at the point 0, I have -2. I'm trying to get it for x. Here's my point, x equals, this is the point 1, -1. That's my critical point. Well, what does it equal where x equals 2? Well, where x equals 2, I have f of 2, so that would equal 2 cubed minus 3 times 2 squared plus 3 times 2 minus 2. So that's equal to 8 minus, well, that's 4 times 3 is 12, plus 6 minus 2. Well, that's equal to 0. So I would have, this is my critical point. I have a point 0, -2, and I have a point 2, 0. So you can see that the graph has to be going like this and not turning around again. Again, because there can only be the one critical point. And if the graph turned around, it would have to be able to turn around again to get back up there. So using the graph and using your graph sense is going to be really helpful for these kind of problems.